Okay, I guess we can get started. So, hello everyone. Welcome back to the DIGA webinar series. So first of all, our apologies for the 1 week delay of this talk, but this was kind of due to unforeseen circumstances. Anyway, it's my pleasure to welcome Ivan Dokmanic to give a talk today. So he's an associate professor in the Department of Mathematics and Computer Science at the University of Basel in Switzerland. He was also an assistant professor at the University of Illinois at Urbana-Champaign, where he still holds an adjunct appointment, I think. And he received his diploma electrical engineering at the University of Zagreb and a PhD diploma at EPFL. Research interests, of course, graph signal processing, all kinds of inverse problems, machine learning, and signal processing in general. He received also several awards, a couple of awards from Google, also Best Student Paper Award at ICASP, and an Outstanding Doctoral Thesis Award at EPFL. And he also got a prestigious ERC starting grant. So it's a pleasure to have you here, Ivan. So go ahead and start your talk. Thanks.
Right. Thank you very much, Gert, for the invitation and giving me this opportunity. And so actually the reason to reschedule is due to unforeseen circumstances on my end. So I'm grateful that we could be so flexible and move by a week. And so the title, as you see, is Understanding and Improving GNNs with the cSBM. Someone just noted, Darina just mentioned that she didn't know that I'm working on graphs. Actually, I don't have too many papers on graph neural nets. That's really true. But I say, my background and my earlier work, as Gert mentioned, is and what my group currently works on is really kind of canonical signal processing with quite a bit of machine learning. We're trying to do both theory and algorithms, and we try to stay close to real applications, real signals, hardware, and so on. I think graph neural nets are really, a very potent tool to work with real data. So the papers that I have written on graph neural nets together with my students are essentially kind of a snapshot of our evolving understanding of the whole thing. So we write papers when we don't understand something and we try to understand. Okay, so I'll talk about, the talk actually has two parts. Both are about using the contextual stochastic block model, which I will introduce to understand and improve neural nets. One is about a paper that appeared in PNAS last year. I was giving talks about it maybe a year and a half ago. And it's about studying generalization very precisely in some simple graph convolution networks. And the second paper is then on operationalizing these insights and trying to come up with new graph rewiring and denoising methods that are based on cSBM and based on signal processing, and that's going to be presented as an oral presentation at this upcoming iClear. So just to bring everyone on the same page, even though I know that I'm preaching to the choir, so the setup for machine learning or graphs is a little bit like this. So in standard supervised learning, there's a set of objects like medical images, people, or paintings, for example, that we want to reason about. And reasoning could be, for example, that we want to know who made these paintings. So we want to solve a labeling or a classification problem. And in this case, this can be either Jean Dubuffet or Georgia O'Keeffe. And the way we want to do this reasoning is by building or learning or selecting a function out of a big set. And this particular function, it does a good job. It is actually correct on all the images. But the point is that we have some large class of functions like neural nets, and we want to pick a good one. So picking a good function means that we have to define a criterion, which, for example, could be that we want functions that learn with few mistakes. And then we have to somehow optimize and solve the problem of looking for these functions. So ideally, we'd minimize the probability that we make a mistake. However, this is the standard issue in machine learning, is that we never really know this probability. So what we can actually do is we minimize the number of mistakes that our function makes on some training set. And we hope that this function that, for example, minimizes the number of misclassifications in some museum in Basel will also maybe work well in Zurich. Okay, so now there's this richer class of problems that everyone here knows more about probably than I do, which are problems where, in addition to these objects, to these data points, there is some relational semantics, right? Some of these data points are in some relationships, They're connected by some edges that could encode all sorts of different things. Maybe they're made, around the same time. They use a similar color map. They use similar canvas. Similar technique. Whatever. There's all sorts of things that these edges could encode. A great variety, and then of course we model these kind of data sets using combinatorial graphs, and features are some functions on the nodes of these graphs. And of course, as always, we will encode these graphs using adjacency matrices and so on. So I don't, again, preaching to the choir one more time. I don't have to tell you that this is important. You've been hearing about it in every single talk in this seminar series so far. But there's certainly a huge number. So this is an old slide I made. There's a huge number of such important data sets. Some of the really nice ones are, for example, protein-drug interaction data sets or protein-protein. You have a data set of molecules. Each one of these molecules comes with a feature vector, for example, the molecular structure, if it's a protein, the amino acid structure, or the 3D shape of a protein. But you also know that many of these proteins or many of these molecules interact or don't interact, which gives you a graph. And this graph is useful for all sorts of interesting downstream machine learning tasks. Okay, so the problem that I'll be interested in this talk is node classification, and in particular something that we call transductive node classification. And so in transductive node classification, we have the usual, we have the graph, the features, and we have the labels. Features and labels are some functions on the nodes. I'll be considering some f-dimensional features. And now transductive node classification, or this problem on the graph, is very, very different from the usual supervised classification, inductive, in that we're given all the possible data there is, right? So we're given both the graph and actually the entire graph. We're given the entire feature function, but what we don't have the complete knowledge of are labels. So we're only giving labels for a subset of vertices in the graph. And the task of this transductive node classification is to estimate labels in the remainder of the graph. This is sometimes also called semi-supervised, although that's not completely, it's only semi-accurate. So the right way to refer to this is transductive learning. And just to give you an example of a typical benchmark data set, which is not necessarily the best thing to work on, but it's something that we always try to apply our algorithms to. So that's a data set that's called Cora. It's a data set of computer science papers and their citations. So there's about 2,700 papers. 5,500 edges, which encode citations. There are 7 classes, so you can solve a classification problem here that corresponds to different computer science topics. And the feature vector is actually quite long because it corresponds to some kind of a multi-hot encoding of some bag of words, representation of these documents, right? So this feature vector is very high dimensional, but maybe there is not 1,500 independent dimensions there, just to get a sense of the problems. Of course, we also work with much larger graphs and also with smaller graphs. Now, in the first part of the talk, I'll be interested in some theory of learning on graphs. And in the early days of graph neural nets, people predominantly talked about their approximation power. The similar situation is for standard feed-forward neural networks, where we talked a lot about universal approximation theorems. And there were all these really beautiful results that connected to foundational topics in computer science, things like graph isomorphism tests, and that established the limits of expressivity of different styles and kinds of graph functions. I would rather be interested in statistical guarantees or generalization. I want to know, when we have some training data, meaning we have some graph and we see some number of labels or some nodes in this graph, what can we say about best possible generalization to unseen labels? And it will, of course, depend on how many labels we actually see and what the links in this graph mean, how good the data is, and so on. So there have been a number of empirical studies on this problem, and also a number of studies that use kind of big hammer tools from statistical learning theory. I think it's useful to just pause or just think a little bit about what is the kind of questions that traditional statistical learning theory is trying to answer. So as I said, we in machine learning, we're trying to choose our function from a large set of functions. And if we could, we would pick one, for example, in this simple case that minimizes the number of mistakes, the probability that we make a mistake. And unfortunately, we don't know this probability distribution. Even if we did know it, which we never do, it would not necessarily admit the easy optimization. So in general, what we do is we try to minimize the number of mistakes our function makes on some data set with some labels. Right? And so certainly this function here, f hat star, will make more, the probability of mistake by definition of this function will be larger than the probability that this f star makes a mistake. And statistical learning theory is about bounding this gap, which is called sometimes generalization gap. It's trying to say how much worse we are because we work with n samples and not infinitely many samples. And so this is usually upper bounded then by some term that's just inevitable that depends on the variance, that encodes the variance, depends on the number, on the size of the data set. This should be capital N. And then on some term that encodes the complexity of our hypothesis class. If we only work with constant functions, then maybe we don't need so many examples to actually estimate the value of this one constant. But for a large neural net, actually, then we maybe need many parameters. And now this is beautiful theory, right? There are many complexity measures that you heard about, like Watnick-Chervonenkiv's dimension, Rademacher complexities, Gaussian widths, covering numbers, different entropy numbers, etc. So it's beautiful theory because it's very general. It applies to nearly every problem, but the issue with this theory is that when it comes to really highly parameterized models like deep neural nets, it often gives vacuous bounds. And the last 10 years of statistical learning theory have been about trying to fix this, trying to come up with definitions of complexity that in some ways don't suffer from this problem. And there's also been beautiful work on specifically transductive notions of these complexities. However, when you apply them to real problems, the issue is that you usually get bounds, upper bounds that are quite loose and that don't really reflect the underlying phenomenology of learning that you're interested in, which is a pity because the phenomenology of transductive learning is in some sense richer than, as I said, inductive learning. So the standard stuff that we deal with in SLT is, we have some amount of data, the data contains maybe some noise, and the hypothesis class is of certain size and complexity. But on graphs, we have, also the quality of the graph. The graph could be poor, it could be noisy. Then links in a graph can encode all sorts of different things. So there's different relational semantics that change the way we learn on graphs. And there's really no role played anymore by the quantity of data because we always have the entire graph in a node classification problem, and we always have all the features. What is now important is what is the proportion of labels about this graph that we know about the nodes. So one example of a phenomenon that this kind of SLT big hammers don't really say anything about is double descent. So this is this new and also old observation that it relates to the bias variance trade-off. If you have a lot of data and you increase complexity of your models, for a while, the more complex the models are, your error will be going down. Now, at some point, your models will be so complex that you will not have enough data to determine the parameters correctly, so your error will start going up because of the variance. And this is the standard law. Now, what we know today is that if you keep increasing the complexity of your models, in some cases, it'll so happen that the error will start decreasing again. Sometimes it'll become smaller than the smallest error in this first descent, and that's called double descent. And actually, some recent papers say that there is no double descent in GNS, which of course, or not of course, but which does not seem to be true. So that's something that we would like to understand. Another kind of phenomenon that or aspect of learning of graphs that we would like to encode is that links can mean very different things. And so two kind of extreme examples are something that we call associative and disassociative graphs, or homophilic and heterophilic. So in homophilic graphs, similar entities connect. So for example, if Gert knows Xiaowen and I know Xiaowen, then in an associative graph, chances are that also I know Gert knows me. Right? It's also so transitive, and we get graphs with a lot of triangles. But in disassociative graphs or heterophilic, different things tend to connect. So we could have a ligand and a protein, and they interact. So there is an edge. In this graph now, if the protein undergoes a small mutation and it didn't interact with itself in the first place, chances are it's still not going to interact with itself, but it'll interact with the ligand. And if the ligand undergoes a small mutation, chances are it's not going to interact with itself, but it's going to interact with the two proteins. And so now you see that instead of getting a lot of triangles, get a lot of these even length loops. And so this the kinds of graphs have totally different qualitative properties. So we expect that learning behaves differently. And indeed it does. It's much easier to learn empirically, at least on associative than on disassociative graphs. So the theory should also say something about that. Okay, so what's an alternative? An alternative, is something that physicists have been doing in the context of signal processing, and then later machine learning, I guess since the late 80s, and it's to analyze a concrete model. So instead of saying that we want to build a theory that works for a huge range of possible hypothesis classes and any distribution of data, we actually want a theory for a concrete model that's often a simple one, and for a concrete data generating distribution that's sometimes Gaussian, a Gaussian mixture. There are many examples that are more recent. We had similar analysis in price sensing using things like Gaussian comparison lemmas and convex Gaussian min-max theorems. For random feature regression, we have precise analysis based on random matrix theory for GMMs, spike covariance models, and so on. And so this is what this is kind of analysis that we would like to do also for graph neural nets. Now the question is, what is the right model to look at? Right random generative model, the simplest thing that we could look at graphs. And so the premise of this talk is that a really, really good one is the contextual stochastic block model. Now, I guess a lot of you know about stochastic block models and their contextual versions. So just a few words. Stochastic block models go back to early 80s. They appeared in many different communities like social science, computer science, somewhat independently. And a stochastic block model is sort of a GMM, like a stochastic block model to the Erdős-Rényi random graph is what the Gaussian mixture model is to a Gaussian, right? So an Erdős-Rényi random graph has pairs of nodes connect independently at random with some probability p. So in a stochastic block model, vertices of a graph are split into different communities, and pairs of vertices connect still independently at random, but probability of them connecting depends on community membership. So if the nodes in particular are in the same community, you get one probability of connection across communities, different probabilities. The simplest case is two communities and symmetric connections, then you can write down a simple formula. And that's actually the case we will analyze. Okay, so let's like now narrow down to a simple case where we only have two communities. We have two kinds of labels, plus ones and minus ones. Those are the yi's here. And then we have a very, very kind of peculiar but very useful parameterization of connection probabilities. So if two vertices happen to be in the same class, then the probability of connection is proportional to some number C in, and it scales inversely proportional with the size of the graph. And otherwise, it's C out divided by the same thing. And the reason to define it that way is that we can then relate it to average node degree. Okay, so we parameterize C in as some average node degree D plus square root D times some lambda, and C out similar but minus square root D times lambda. So let me try to explain, like kind of or interpret this parameterization for you. If you imagine that this lambda is large, for example, it's square root D, then this term here is D, and you get that the probability that you connect nodes in different communities is 0, right? So this makes the problem particularly simple, because if you're trying to label nodes according to their community membership, well, actually, you just look, the graph here is disconnected. It has two connected components. So you just check in which connected component you are. Okay, so lambda plays the role of signal to noise ratio in the graph, and the larger the lambda, the easier the problem is, the better the signal to noise ratio. If lambda is 0, you get Erdős-Rényi random graphs because everything connects with the same probability. And the really cute thing is that you can take lambda to be negative. If you take lambda to be negative, then actually you have a higher probability that nodes connect when they are in different communities than when they're in the same community. So this generates an interesting phenomenology. We have all of these knobs that week, which is great for analysis. Okay, and so here are some examples. If a graph is like totally homophilic, basically C out is 0, then really it splits into two components. A heterophilic graph, typically nodes of different communities connect. And both extremes are in some sense, one extreme is disconnected, the other extreme is bipartite, they're simple. Now, contextuality comes, when we do graph neural nets, graph convolution networks, etc., we want to analyze them, we would also like to have some features. And so here's a really natural way to define features. Now, to each node, we'll associate a feature vector, which is f-dimensional. We call it xi. And this feature vector can be in the direction of some vector q. So q is an f-dimensional vector, or in the direction of minus q, if yi happens to be -1. Okay, so basically our features are either plus q or minus q, corrupted with some Gaussian noise. Okay, so this is a latent Gaussian mixture model. We don't know q, we don't know this direction. It's part of the problem. But what we do have is we do have, again, some kind of a signal-to-noise ratio knob. It's called mu. If mu is 0, then features are just pure noise, and the problem, I mean, features don't help you at all. If mu is very large, then features are dominated by these terms that encode the labels, and the problem is presumably. All right. So let's summarize. Oh, before summarizing the situation, okay, so clearly, I mean, in this talk, I'll be using this cSBM, hopefully to say some interesting things about graphs. But the great thing about having a generative model like that is that, when we usually write papers about GNNs, we come up with a new algorithm, we apply it to the usual benchmarks, we improve them hopefully, but then we don't really have an idea of how much headroom there is, right? We don't really know what is the best possible algorithm doing on these data sets, like Cora or any other data set. And the great thing about having something like cSBM is that there are all sorts of fundamental detection bounds. And there exists an algorithm that is conjectured and believed to be optimal, which is belief propagation. So we can get somehow best possible results, and then we can compare all algorithms against theoretically the best possible result, which is a very useful thing to have. This has been used to analyze GNNs, in particular in cases that I'll call strong signal or linearly separable cases. We'll look at a harder scenario, which is a weak signal case where features are, and everything else is not linearly separable. And it's been used, cSBM is starting to be used quite a bit, indeed, to obtain empirical results, as a benchmark, as a litmus test of a quality of an algorithm relative to, a really strong baseline. Now, I wanted to say something more about it, and so I came up with this figure. Actually, I should say my student Cheng Shi came up with it, and then we tried to because this figure is not very easy to explain, but I will nonetheless try because I think it's very useful, and it shows a way in which the contextual stochastic block model is somehow universal. Okay, so again, like this graph contains all sorts of standard benchmark graph data sets that we use to test algorithms. Some of them are heterophilic, some of them are homophilic. This is not so important, but this is encoded in the color of this bubble. Now, what I'm plotting on the abscissa is something that we call the absolute homophily score. This score tells us how, basically it's the lambda. It's somehow related to lambda, okay? It's not exactly lambda. And if this is large, this means that the graph SNR is large and the problem is somewhat simple. If this is small, the problem is hard, at least as far as the graph goes. Now, again, when you're doing node classification on graphs and writing a paper, you have to decide how many vertices in any of these graphs you'll use to train your graph neural network, right? This is just a decision that you make, and hopefully, you make it in a way that enables you to compare with other papers. Now, people talk about something that's called a dense split and something that's called a sparse split. Sparse split means you use a very small number of labels, like 2 or 3% to train. A dense split means you're using a lot of labels, like 60% of all the labels to train your network. Okay? And what I'm plotting on the ordinate is the difference in performance, in accuracy, a relative one, between a given algorithm, which in this case is a GPR-GNN, a really good convolution-style graph neural net, when it's used with a dense split versus when it's used with a sparse split, right? So this shows me how much better. Let me try to highlight it. This shows how much better I'm doing when I train a network on a dense split versus on a sparse split. Okay, and you see that there's some kind of a regularity, right? So there seems to be somehow some regularity in how data sets behave according to it. In particular, if the problem is easy, you don't gain much by using the dense split, right? But if the problem is hard, then having a lot of labels is good. Now, what are the two curves, the dashed lines? Dashed lines are actually cSBM, and it's two different algorithms. So one is some very, very, very simple GCN. The other one is GPR-GNN. And you can see that cSBM is really representative of the behavior of real networks on real data in this sense, right? So these two algorithms, in absolute terms, they're very, very different. One is much better, GPR, GNN. But in this relative sense, it seems that cSBM is really telling us something interesting about the value of labels for solving a node classification problem on a graph. Okay, so it took me a while, but hopefully it's somewhat clear what this graph is showing, right? So it's another justification to look at cSBM. All right, so I want to use this to first say something about the generalization, and then to come up with the denoising and rewiring algorithm. Okay, so for generalization, I'll look at a simple architecture that, again, everyone here knows probably more about than I do. It's a graph convolution network. And the graph convolution network is a particular message passing graph network. So I'll just set things up for the sake of like establishing some notations. So here we have a graph, and each vertex has some associated feature vector. We're interested in how the feature vector for this central vertex is being updated. The way to do it is in a graph convolution network is you multiply. So first you compute some messages for all the neighbors of this central node. The way you compute this in a graph convolution network is just by multiplying the feature vectors of these neighbors by matrix. And then you update x1 simply by summing this or averaging, or you could also include a self loop, etc. So this is the update equation, the usual one. And if you look at this for 30 seconds, you can see that if you collect all the feature vectors for all the nodes in the rows of some matrix X, then you can write this update equation for the whole graph at once, like this. So it's a multiplication between three matrices. So you have the graph, the features, and then the weights. Okay, and so the features are propagated across the graph by a left multiplication, and then weighted by the weights on the right, and then you hit this with some nonlinear activations. We'll simplify this even further by removing activations. Now, of course, people will scream and be outraged at this, and rightly so, because if we remove nonlinear activations in a standard feed-forward neural net, then the function just collapses to a linear function. And in some sense, at least representationally, it's not interesting anymore. We just get Wiener filters. However, the situation is very different in graph convolution networks. It doesn't happen there. This has been shown empirically and in a beautiful paper, which is called Simplifying Graph Convolution Networks from a couple of years ago. And my intuition, which has something to do with reality, just to try to explain why this is the case, why removing nonlinear activations doesn't hurt too much, is that in graph learning, both the features X and the graph A are themselves part of the input, right? And here we multiply them. So we're multiplying two pieces of input, which is simply not a linear operation. This is not linear in the input. Moreover, A is often constructed from features or from something that's related to features using some kernels and thresholding, etc. And then you can see that this is totally nonlinear. Okay. Think about spectral clustering. Spectral clustering, implemented by power method, it just involves multiplying things by the graph. Right? So this is not linear. Okay. So let's see then. So once we remove these nonlinear activations, our network is basically a polynomial of the adjacency matrix, and it only makes sense then to have a weight vector which directly maps things, the inputs to labels. This is this polynomial. We'll be interested in large graphs, so we'll look at the scaling when the number of nodes and the feature dimension go off to infinity, in such a way that the ratio between the size of the graph and the feature dimension converges to gamma. This is a hard regime, and kind of a post hoc justification for this regime is that it's a good one because the phenomenology that we discover is actually close to what we've seen in real graphs, and I'll argue about that. We can work in a very, very sparse regime, but not the sparsest possible. We need to allow the average node degree to also diverge to infinity, but it can do so very, very slowly. Okay, so the point is it doesn't have to be any power. It can be a log of the size of the graph. It just has to go to infinity. Now, in this setting, because the only thing that we're learning is W, we'll fit our labels, again, for simplicity, using the least squares loss. And so this is a nice convex loss. Actually, there's a unique solution that we can compute in closed form. All right. And so just to summarize, what are the knobs, that we now have in our analysis that we can, hopefully analyze? Well, there's the graph SNR, lambda, that also is signed. There's the feature SNR, mu. We have alpha, which is the ratio of the feature dimension to the size of the graph, and its inverse gamma. Tau is what percent of vertices we know the labels for, and there's some regularization parameter, which is less important. And two extremes, if graph SNR is 0, we get a GMM. If feature SNR is 0, we have a stochastic block model. Okay. Or at least, yeah, I think, I'm not sure. Yeah, something like that. So here's a perspective that will also be useful for the second part of my talk that I think is useful to think about this problem. And so one way to think about this problem is that what we really are interested in are labels for our data points. And now these labels are this latent unobserved thing, and these labels go into two different independent channels. One channel is an SBM channel, and it generates the graph. The other channel is just like kind of a GMM channel, and it generates the features. But the thing is that these two channels, the noise in these two channels is independent. And so there is hope that by kind of constructively using both independent sources or views of our information, we can do better than by using either one alone. So the kind of analysis that will run for this goes back again a long time to the theory of spin glasses, things like Ising models, and people have done this for a long time in physics, and now very often we see this kind of analysis also in signal processing and machine learning. So basically, the idea is that our graph, we see it as a system of interacting particles that involves in some energy that's defined by the loss function. In physics, this energy is something that's called a Hamiltonian. This one here is for something that's called the Ising spin glass model that's been used to study ferromagnetism. And the analysis goes through a construction of something that's called the Gibbs distribution, or the Gibbs measure. Now, the Gibbs measure is simply a probability distribution that assigns higher probabilities to configurations, here denoted by sigma, right, of spins, that achieve a lower energy, which makes sense, right? Nature wants to go to states of low energy, so they should occur with higher probability. And beta encodes temperature. So beta is something that we call the inverse temperature. So if beta is very, very large, you can see from here that this means that, sorry, if beta is very small, this means that the inverse temperature is the temperature is very large, and the probability distribution becomes very diffuse. So many states have similar probabilities because of thermal fluctuations. But if beta becomes very large, then this is kind of a soft min function. It starts to concentrate on the minima of the energy. Okay, and I'll go quickly here, but this is not our idea. So as I said, many people have done similar things in signal processing and image processing and machine learning. Legendary paper, from '84, Gamma and Gamma on Markov random fields, to analysis, compressed sensing, and so on. Okay, so here's more concretely our energy, our Hamiltonian. This is simply the loss function. The weights here set up the parameters of the universe in which our particles live, and we're trying to find the most probable universe. In some sense, it explains our observations. I construct the Gibbs distribution in very much the same way, and the really important thing is what we call the partition function, which normalizes this Gibbs distribution. It turns out that this partition function really encodes kind of all information that we need to know in order to solve our problem. And as I said, the idea is that as the temperature goes down to 0, this object starts to concentrate on global minima. Now, given the fact that our Hamiltonian is convex, actually strongly convex here with regularization, there's a unique global minimum, and this is what we're going to get when we set temperature to 0. So the program is that we do the analysis at a finite temperature because that is easier analytically, and then once we have a result, we send temperature to 0. Now, in the interest of time, I'll skip the analysis. I'm very happy to discuss it. I like to talk about it very much, but I'll kind of try to fast forward a bit to results. I'll only say that the analysis is physics style that we've done. It's based on something that's called the replica method in physics. It's been pioneered in the analysis of rubbers by a guy whose name is Sam Edwards, who heard about it from Mark Koch, who was actually a mathematician, and he would never use it because it's not rigorous. It's actually impossible to prove anything about it. But it's been, maybe most famously used by Giorgio Parisi in a series of papers. It's kind of a very sophisticated version of this analysis in a series of papers on the analysis of disordered systems that eventually earned him the Nobel Prize in physics a couple of years ago. So it's an important tool in analysis of disordered systems. Okay, so maybe I will me just see how much time I have. Okay, so let me just say, in the middle of this analysis, what you have to do is you have to, just to give you a glimpse very briefly, is you look at the powers here of your partition function. You remember that partition function was just related to the normalizer that gives distribution, and you want to compute expectations of the powers of this partition function over some of these order parameters. And the thing is that you end up with somewhat ugly expressions like this. How are you supposed to compute these expectations? Now, if you look at a little bit these kind of expressions, this is the kind of problems that you can solve if the argument of this norm here is jointly Gaussian vector, right? So if this argument is some vector that has a jointly Gaussian distribution, then actually we can compute these expectations in closed form. Okay, we have a formula. However, this here is related to some binary adjacency matrices, etc. This is definitely not jointly Gaussian. Now, the whole argument hinges on showing that as the system becomes larger and larger, you can appeal to some form of the central limit theorem to argue that this is becoming more and more Gaussian. And so in the limit of very large graphs, actually, we can use Gaussian formulas. Okay, so that's the universality argument. We have a conjecture in the paper that we believe is true. We tested it numerically that this universality is in some sense true for our problem. I'm again very happy to discuss, but I'll just keep steaming ahead and skip this for the moment. Now, okay, so what does a typical result look like? A typical result is very different from what you get by applying results from statistical learning theory. I think my mouse will die. So I'm just sorry about this. I need to plug in my mouse, otherwise I'll lose the ability to interact with my computer. Okay, it's done. So here's a typical result. Like a typical result has an equality sign, right? So this is not a bound. This is really a formula, an exact formula for the test risk. And as you can see, it's a relatively simple formula of the parameters of our problem. Fraction of labels that we're using, oversampling ratio, SNR of the features, SNR of the graph. It's pretty great, right? I mean, because it's just exact, it's precise. And you can get similar formulas in more complicated cases, or if you don't get a formula, then you get some sort of a saddle point equation that you can solve in a microsecond, but essentially you have a very precise characterization. And so examples of plots against the training ratio. So what you're interested in is some kind of error, training error or test error against the training ratio. So the crosses here, they're actually trained networks. Performance of trained networks are finite size, like 1,000 nodes. And the dashed lines are the theoretical curves. And as you can see, they're an excellent agreement, which is pleasing and nice. And then you can really start looking at the phenomenology, right? So here you see that as you're increasing the number of labels that you have for training, your error first starts going down, but then in some cases it starts going up again. Okay, so that's absurd. You're giving more data to your learning algorithm, and it performs worse and worse the more data it has, and then it goes down again. Right? So this is actually a phenomenon that we understand well today. It's called double descent. It's a bit of an unusual way to look at it because we're not varying the complexity of our estimators. We're varying the number of labels that we have for training. That is the same thing. And once you know what to look for, you can actually discover this double descent in real graphs for a variety of algorithms. So all of these things show. So for example, blue curves here are losses. You can see that you're increasing the number of labels, the losses go up, and then the losses go down. So it actually happens with real networks and real graphs. And just a brief kind of signal processing note, which I really like. So if you look at what people do for graph convolution networks, they often introduce self loops because it turns out that on homophilic data, if you connect every node to itself, then your network, you get better performance. Right? It's actually a really simple signal processing explanation. But for heterophilic data, people just don't, practitioners just turn off self loops because for heterophilic data, this hurts performance. Okay? Well, we can understand that using our analysis now, because lambda, the sign of lambda, actually, we can just see what happens when lambda is positive or lambda is negative. When lambda is negative, we have heterophilic graphs. And then what we've done is we actually tune the self-loop strength here. We don't just add identity, but actually add a scale identity, and we allow it to also be negative. Now you see that if lambda is negative, you have a heterophilic graph, then best performance, meaning smallest test error, happens when you have a negative self-loop. Okay, so that's not something that normally you do, but you should if you want to get good, well-performing networks. And actually, we test this on real data like chameleon and squirrel, which are heterophilic data sets. And you see that if you add self-loops with negative weights, you get best possible performance. So that's interesting because there is a simple signal processing explanation involving graph spectra, which again, in the interest of time, with apologies, I will skip. But I'll say the following. Actually, there's an even simpler signal processing explanation, which I guess many of you already know, which is that a self-loop, so A plus identity, really corresponds to a simple two-step filter, which is identity is just a one, plus one and zero, and A is a delay, so you get the 1, 1. Now, everyone knows from DSP 101 that this filter here is a low-pass filter, right? So low-pass filters are really good for homophilic data because homophilic data is low-pass on the graph. This filter here, which is A minus identity, everyone who took signal processing knows that this is a high-pass filter, so this is good for heterophilic data, which is high-pass on the graph. So this is not a great surprise. But it's interesting to see that this comes out of this crazy analysis. Okay, so, and this is maybe the very last thing about this, and then I try to quickly present the second part, which is that, the great thing about cSBM is that we have fundamental limits. So for planted GMM, which is, without a graph, we actually know that detection better than random is possible in an unsupervised sense when the SNR of your GMM is sufficiently high. For the stochastic block model, we know that we can get better than random classification of nodes when the graph SNR is sufficiently high, larger than 1. And for cSBM, when some combination, actually the sum of these two SNRs is sufficiently high, we get better performance. And so when you have an analysis like the one that we have here, you can actually ask, what if I take a really, really, really simple algorithm, like a single layer graph convolution network, and I give it a few labels, can I beat the best possible unsupervised algorithm? Okay, and you can actually answer this question by increasing the number of labels, and then what this plot is showing for different graph SNRs and different feature SNRs is for how many labels you start performing as well as the best possible unsupervised algorithm. It actually really tells you the value of labels, and you can see that in some cases you actually need very few labels to perform as well as the best, optimal unsupervised algorithm. Okay, so I really like this takeaway. Okay, there are many, many takeaways that I could talk about still, but then I will not have time to briefly present the second part, which is about graph rewiring, using this perspective for graph rewiring. All right, so I can go a bit faster because I think a lot of people here know about rewiring. But what is the idea? The idea is that even if your graph correctly encodes interactions, has all the correct edges, it may not be a good graph for a given algorithm, like a message passing GNN. Okay? Because maybe message passing GNN then cannot compute certain functions. And so the idea of graph rewiring is that you first somehow pre-process the graph by adding and removing edges, and only then do you feed it to a GNN. And it seems crazy, but it works. Okay, so here's an example from a recent paper that's one of the landmark papers on this topic, which shows that there is a link actually with geometric notions on manifolds like Riemannian manifolds, such as Ricci curvature. It's basically like what they show is that edges like this one here, which fan out, which are kind of lonely, and then they fan out a lot. These edges correspond to some negative curvature on a corresponding manifold, and they act as bottlenecks. And so if you can find those edges, the good idea is to kind of bolster them by more edges, and this prevents something known as over-squashing of messages, and actually improves performance of downstream GNNs. Now, when I looked at this, I thought it's very aesthetic, very beautiful, but one thing that I just couldn't wrap my head around was the fact that this graph here is like an easy peasy graph for spectral clustering. Right? If really like this graph, so this here corresponds to one community, the other half corresponds to the other community, then this is actually an excellent situation for simple spectral clustering. And this is a little bit harder for spectral clustering, but it seems to be the other way around for a GNN. And the argument is that the reason why you want to do this is because maybe there are important long-range interactions that can then not pass through this bottleneck. So the question is, why would there be long-range interactions? And this can happen if you have same labels on both sides, right? But then the meaning of this graph is kind of questioned. What is your graph encode? So we looked at that through the lens of the cSBM. And we ask, so what are the reasons for a GNN to underperform? One is this geometric, that there are bottlenecks and over-squashing and also over-smoothing. The other reason is that it could be that simply graphs are very noisy, features are very noisy, and GNNs are simply not expressive enough to compute your, bias classifiers and best denoisers locally, even when they are local, right? It's just that there's a lot of noise and they're just not expressive enough. So we tried to see what happens if we interpret graph rewiring as a simple denoising problem rather than, a geometric problem. And, also use features, right? So we actually cheat a bit and we say we're going to use more information. We're going to also use features. Okay, so you remember this figure, right? We have the labels, we don't see them. They go into two different channels. One generates the graph, the other one the features. So let's try to simplify this. Okay, a much simpler situation is we have a number. We call it a mean, mu. Okay, we would like to estimate this number. It's a message. This message goes into two different Gaussian channels. They're independent, but they're the same otherwise. That add zero mean Gaussian noise to this number, and we end up with two Gaussian independent random variables that have the same distribution, mean mu, and variance sigma square. Okay, so now you can ask, given these two independent views of my mean, what is the best estimate of the mean? And so you can choose a criterion like MMSC with some uninformative prior, or minimum variance and biased estimator. I mean, whatever kind of reasonable criterion you choose. The answer is that the average of x1 and x2, so the empirical mean, is the best estimate of mu in many, many, many different senses. Okay, so can we come up with something that's just that simple for graphs? Okay, so here's the intuition for when we have two communities. When you have two communities, remember that this y here is a vector of labels that contains plus ones and minus ones. So the expected value of our feature matrix is really this rank 1 matrix here. This column space really tells us everything about labels. Right? Something similar is true for the graph. So because the graph is an SBM graph, the expected adjacency matrix has a simple block structure. Right? The off-diagonal blocks tell us about the out of community connections. The diagonal blocks are inside community. And you can write this down. I mean, you can see that this is actually a simple rank 2 matrix. Okay, so there's some top eigenvector that's not very informative, just a constant eigenvector, and then we have something that also has labels in column space. Right? So we can actually look at we can subtract this first eigenvector. I call this E expectation of A bar. That's only only about labels. Okay. So let's try to use this to build an algorithm. Morally, our A bar is something that, I mean, morally, so I put quote marks here, is something that, has labels in its column space plus some noise. And X is morally also something that has labels in its column space plus some noise. So, of course, if you just do an eigendecomposition of A, you're not just going to get labels. You're gonna get some eigenvector that combines labels and this noise, right? So it's, this noise will kind of pour into this eigenvector. Right? But both eigenvectors are hopefully somewhat both of left singular vector of first left singular vector of x and the top eigenvector of A bar are related to labels. Right? So this is the idea that somehow this we want to combine these things in some way. But it wouldn't just make sense to average them because we don't really know these SNRs. We don't just want to estimate labels using some spectral clustering. We actually want to modify the graph. We want to rewire. And what if there are more than two classes? If there are more than two classes, actually there's top k eigenvectors that contain information about the graph. Now, if you look at the original cSBM paper, they analyze this optimization problem. Okay, this optimization problem looks like a combination of two variational characterizations here of eigenvectors or eigenvalues of A, and here of singular values of X. Okay, so U and V are unit vectors, and you actually get the second leading eigenvector of A because you ask, that V be approximately orthogonal to all ones. So you're going to avoid the first one. Okay, and if you think about, what is optimizing this, well, the first term is optimized by the leading eigenvector of A, the second term by the leading left singular vector of X, and then this somehow, if you nail the right B, this kind of combines information from both. Right? So we want to build on this, but for more, for many classes and build a practical algorithm, right? So as I said, when we have more than two classes, then we need to look at the top k singular vectors. Apologies for rushing. And instead of looking at this complicated thing, actually, we look at something that we call alignment. Okay. So alignment is we take the top L singular vectors of the graph and the top L left singular vectors of the features, and we compute an angle between the corresponding subspaces. So this expression here actually gives you the cosine of the largest principal angle between these two subspaces, explained by the graph and by the features, and it's a measure of alignment. Okay, that's why we call it alignment. Okay, so here's quickly a full algorithm that looks completely ad hoc, but actually it works. Right? So the algorithm is that you're given a graph, you're given features, you eigendecompose them, and then for every of the top L eigenvectors of the graph, you look for the closest left singular vector of the features, and you do an interpolation between the two. But you do a gentle interpolation. So you take this eta that is this is a small number, right? Such that you don't deviate too much from the initial graph. And this eta is determined as a hyperparameter. Okay? Once you do this interpolation, you resynthesize the graph and the features. You can round the graph, and then you run the procedure again for some number of iterations. Okay, so here's some, I skip this. So does this improve alignment? That's the first question that you can ask, because it's a completely heuristic argument. And so in the paper, we have a theoretical argument. We have a proposition that actually shows that it does improve alignment. And we can actually run an experiment. Okay, so on cSBM, you can somehow summarize the lambda and the mu and all the parameters of cSBM in a number. This I lifted from the GPR-GNN paper. And so this phi varies between +1 and -1. So +1 is a very homophilic situation, -1 is a very heterophilic situation. Okay. And so you can see that when we run our JDR algorithm, joint denoising and rewiring, actually alignment improves by a lot, right? So this is a random instance of cSBM, and this is after running JDR. So really, this algorithm does improve alignment. The second test is, okay, let's now run actually this algorithm on cSBM and then put it into some downstream network, like a GCN or a GPR-GNN. And the great thing about this is, again, that we have an optimal estimator, right? So this curve here is a result of belief propagation. Okay? And that's the best possible estimator. It's optimal. Okay. And so the green curve is only using features using an MLP, ignoring the graph completely. Okay, it doesn't work well when the graph is good on the sides. And here now for a graph convolution network, you see that the GCN performs very poorly for heterophilic graphs. We know that from before. And it kind of performs okay for homophilic graphs. But the blue curve is GCN after using JDR. And you can see that the performance is really great. I mean, it really improves it by a lot. So a simple GCN performs quite close to the optimal estimator after running JDR. You can do the same for GPR-GNN. And again, the blue curve is improved in this case when the graph is weak, but the features are good. Now we can run this also on real data or real benchmark data sets from real situations. And we've done this on a huge number of things because reviewers asked us for it. And the bottom line is that actually JDR generally outperforms all other rewiring algorithms. Of course, it uses more information. It's using features which other rewiring algorithms don't use. But the nice thing or the interesting thing or an intriguing thing is that this is true by using only a denoising perspective. We're simply just trying to remove noise from the graph and from the features. Same thing is true in heterophilic data. There are in some cases, actually some algorithms outperform it. This is usually the case when the graph is really bad to begin with. But if we combine it with GPR-GNN, then it's really good. Okay, so some food for thoughts. Okay, this brings me to my last slide. Closing thoughts. So I think there's a lot of value in actually using cSBM and still a lot of potential to think about signal processing on graphs. I'm really surprised, that there are no great ports of belief propagation that are learnable, and I believe that there's a big gap there, algorithmic, that we could improve performance a lot by looking a little bit into physics. Another thing is that I think, and I know that some people, I've been actually talking with Xiao and Dong last week, who told me about their work on understanding long-range interactions. So I think this conversation is starting. But all of this kind of over-smoothing and over-squashing stuff, I think this is important when long-range interactions are important, but it seems that this is not the leading order issue in many of the real node classification problems. The leading order issue is actually noise. At least this is what I currently tend to believe based on our results. And finally, I think that this combination of signal processing and physics is a really cool and neat toolbox to apply. And there are many other things to analyze, depth, nonlinearities, etc. Other people have already, like the group of Lenkas Deboto, have already greatly extended our results, and so I look forward to working on that in the future. Thank you.
Thanks a lot, Ivan, for the great talk. Very interesting. Yeah, so let's see if there are any questions. So feel free either to put them in the chat or to unmute yourself and ask the question. So there was one already in the chat in the beginning about how do you find the topological signal strength? I guess that was in the beginning, but it's kind of just a parameter that you tune, right, for the analysis.
Yeah,
It's not something.
Yeah. It's part of the distribution. It's like the variance of SBM. So it's it goes into our analysis.
Right. Of course, for certain data sets, you could check how big it is, right? So you can estimate it somehow, or
yeah. So if we have, in particular, if you have a realization of cSBM or SBM, you can estimate lambda. In some cases, it's easy to estimate it in like a strong signal scenario when it's very large, and then it's simple. When it's weak, I guess you can still estimate it, but you need to do some sort of Bayesian estimation. So you need to do it carefully. You need to run it like maybe a complicated algorithm, but it's possible to estimate it from data in some cases.
Okay, good. Other questions? Someone? So Mohammed has a question. Did you use GNNs with a single hidden layer in your experiments?
So for to do that, like equivalence between labels and optimal unsupervised algorithms, it was just a single layer GNN. In other experiments, in the first part, it was a two-layer GNN. Like a pretty good one. That's decent. In many experiments, we used for rewiring GPR GNN. Yeah, so we used
what is a GPR GNN?
Oh, is this like sorry, I just assumed because okay, that's bad. Yeah, so GPR GNN is this adaptive generalized page rank neural net.
Okay.
It's a little bit like, you know what I mean? It's so in some sense it's the right thing to do from a signal processing point of view, and you can really see that then somehow it's symmetric in high pass, low pass sort of performance. This is a general filter. Yeah.
Because as far as I can see, so your output feature is always single dimensional, right? It's scalar per node, right? Or
oh yeah, in the first part.
Effect.
Yes, correct. Yeah. So in the first part of the talk, because we wanted to calculate, precise analytic expressions, we just used that. In the second part, actually, it works for realistic data. The different feature dimensions, any number of classes.
Right. And so if you would have multiple layers without non-linearities in between, then yeah, you can combine the polynomial somehow, or can you then, does it still make a difference whether you have one big polynomial or many short order polynomials? Like, concatenating short order polynomials, does that help or?
Yeah, I think, and I should check, but I think in that case, and that's again the first part where we just did this for the sake of simplistic analysis. I think it always collapses in the end to polynomial features vector. You can always rewrite it. I'm not 100% sure, but I think it always collapses in it.
Okay.
Yeah. So hi, Ivan. So thanks for a very nice talk. So I'm actually wondering about in the second part when you mentioned about the rewiring thing. So like what I see is that you're actually rewiring one of the eigenvectors in the graph, right?
Yeah.
Yeah. So what
sorry.
kind of rewiring is that actually? I'm wondering.
Yeah. So we're rewiring one eigenvector at a time, but what we iterate. So the algorithm that I showed, maybe I can I should show it again. Just give me a sec. Where are you, algorithm? Here. Okay, so now I need to share. Yeah, so this algorithm here, we iterated. And I think I just said it, I didn't write it. So we do this. Yeah, but also one pass of the algorithm updates all eigenvectors. So here sorry, it's just like a very sloppy slide. Yeah. So I goes from 1 to L. So we go over the top L eigenvectors. We update all of them a little. And then we resynthesize here. And then we do it again. for some prescribed number of iterations as a hyperparameter or prescribed.
Yeah, but
So-
does it destroy the sparsity pattern of the graph eventually?
Exactly, because here we round. Basically we can check exactly, like I think maybe that's what you're suggesting. We can check whether the final graph is somehow similar to the original graph, and it is, because we keep this eta small, and after this update, then we can again binarize this matrix, or we can threshold it, and
Okay.
because we don't allow eta to be large,
Mhm.
then we just in the end the graph is like somehow just a denoised graph, but morally it's the same. Yeah.
I see, but but at some point I think you also mentioned about the theories of for the algorithm, right? So does that the theory depends on the ether or something like? I mean, like what are the trade-off there, for example?
Yeah, the theory. So the theory. The theory just says so. I should have put it on the slide. So the proposition that we have in the paper, which will by the way be updated, right? So in a day or two we'll have a new camera ready version. But already version is already there. It says that I have a cSBM setting. I have my A, my X, and I can take eigenvectors or singular vectors of both.
Okay.
And then there exists a small eta, such if I do this interpolation with a small eta, and then resynthesize, I get something that's better aligned with the labels.
I see. Okay.
So it's a simple result, but it somehow says that this is not going to do something crazy. It's not gonna, it's gonna improve things, right?
Yeah.
Yeah.
Thanks a lot.
Sure.
There was also a question by Yanis on, have you tried different interpolation schemes and checked for algorithmic robustness and consistency?
So I'm not sure exactly what is meant by robustness and consistency. We tried all sorts of interpolation schemes, but this simplest one, which is the simple linear interpolation, works well. We tried things like we say, oh, actually these things are unit norm, right? These eigenvectors. So let's try to do something such that the interpolation, is also unit norm. This doesn't seem to play a big role. Like just manipulating data is already enough. As far as algorithmic robustness and consistency, we really have an outrageous number of experiments in the paper. I felt bad for it's just because the reviewers, although we had already a huge number of experiments to begin with, someone said that we don't have enough experiments. So I think we have like hundreds of different settings and ablations. And so if that is meant by robustness and consistency, in that sense, like we have a variety of settings and comparisons, spectral clustering with different GNNs and many different data sets, 17 or so, 18.
Okay.
I'm not sure if I'm answering any question here, but yeah.
Yes, no. That's what I was aiming at. Can you put is the draft paper on the archive? Can you put the number?
They want to privately donate.
Or is it still not out yet in any public form?
EcoHealth Alliance.
I can do that. So let me see. It is. It's called joint. Let me do this. It was on my first slide. Denoising and the rewiring. I think you can also find it in Open Review, but here's the paper and it'll be updated. So I emphasize it. I put it in the chat.
Yeah, and we'll put the video will be on the Signal Processing Society YouTube channel. So there, I think on the first or the second slide, you put the titles at least of the papers, right? So then you can search for it if people want.
Yeah.
Any other questions?
Maybe I have a question. Thanks, Ivan, for the very, very interesting talk. It's a very open question, so but I thought it would be interesting to get your perspective. So in what you presented in terms of combining physics and GNNs, basically, your perspective was more on the design of your second part of the talk. So designing the rewiring strategy in such a way that you take into account some physics constraints, right? So there is a lot of literature that follow a completely different angle, that is designing neural networks using continuous differential equations, right? What is your input on that? What type of benefits brings one approach or the other? Any comment on
Yeah, I
on that
always
would be interesting.
I wish I could give a really substantial answer. I don't, but I can certainly speculate. So first, I mean, in the second part, physics, there's much more signal processing than physics. It's this idea of resonance that I didn't really maybe emphasize enough. That when you align signals, right, the graph, and you align things, and then the signal peaks. So that is really what happens there. There's not so much physics as in the first part, statistical mechanics, because I mean, we just use inspiration. We take inspiration from cSBM, but yes, and we don't change any algorithms. So it's a rewiring thing. We pre-process and then we put it into some standard off-the-shelf established algorithms. Now, for your question about this architecture that are inspired from PDEs and ODEs, I'm actually trying to understand them, and I think some of these ideas are absolutely great. So I think especially. So a place where I can see that these things are great and that they should not have issues with long versus short range interactions because they're automatically inverting, basically like you're saying, solving a PDE is like inverting a tri-diagonal matrix, but the inverse itself is global, right? So you automatically get long range. I think this is obviously a great idea when graphs are low dimensional, like when you work with meshes or graphs that are sampled from manifolds. Then it makes a lot of sense to me. And what I'm trying to understand is, I think that's one extreme, right? And I'm trying to understand what happens for graphs that are more like the stochastic block model, that are not low dimensional, right? So the spectrum it goes everywhere. There's no underlying manifold. There's no low dimensional structure. It's just like a bunch of stuff. And there exists an algorithm, but it's different from these PDE-inspired algorithms. So if I think about these PDE-inspired algorithms, GNNs, they're like PDE-based image processing, which is a great idea, and then done on graphs. But SBM is really not in any way low-dimensional, so sorry, I'm waffling a bit. But my point is that there exists an optimal algorithm, which is belief propagation, when you know the distribution, right? So there are some situations, if you know it's cSBM, there is an optimal algorithm and it's easy to implement. So to me, it's about interpolating between these two regimes, right? I believe that there must be a really good algorithm that is not exactly the GNN that we're currently using. I'm not the only one who thinks that, right? That navigates this trade-off, right? That goes from like graphs that are basically manifolds or discretizations of manifolds to graphs that are, expanders or crazy things that are definitely not discretizations of manifolds, right? I'm not sure if this is interesting what I said in any way, but yeah.
No, I think it's interesting in any case. I mean, it's a very open question, but I think it's always interesting to hear your perspective. So thanks.
Other questions? If not, then thanks again, Ivan, for the nice talk and for being here today. Actually, our next talk is already next week, so I will try to send the day before a reminder of the talk. So I hope to see you all then next week. And thanks again for your attendance. And you, Ivan, for giving the talk.
Great. Thanks, everyone, and thanks for being